a computer vision-based indoor wayfinding tool from the Coughlin Lab at the Smith-Kettlewell Eye Research Institute in San Francisco. This is a project by James Coughlin and myself, Ryan Crabb. We are creating an indoor navigation tool to help further enable the independence of blind and low vision travelers. The tool is in the form of an app that can be used on a person's own smartphone. While GPS-based navigation is generally reliable and suitable for traveling longer distances in an outdoor setting, once a traveler has entered a building, the GPS signal is often degraded and not precise enough to provide directions in the indoor environment. In our system, we create a digital floor plan of a building, in which we mark the locations of various signs and other visual landmarks that are already present in the building. On this map, we represent the signs with color dots and semicircles to denote the direction in which they are facing. Instead of relying on GPS to determine the user's position, our system uses the phone's camera to detect these visual landmarks and uses them as cues for where on the floor plan the user might be. For example, exit signs are typically posted in visible locations throughout a building. We use the phone's outward-facing camera to scan for signs as the user makes their way through the building. The traveler is able to complete their final leg of their journey independently, even in an unfamiliar setting. With computer vision technology, we are able to train a machine learning algorithm to detect specific objects in an image. Using a few sample pictures of each sign captured by someone in the building, we can train an object detection model using readily available off-the-shelf software. We use the size and location of the detected object in an image to estimate their position relative to the user. Modern smartphones come equipped with powerful sensors that can track how the phone both rotates and moves in 3D space. Once we know the person's position in a building, the algorithm can track their movement in order to give turn-by-turn instructions or some other mode of auditory guidance. We can see here how the position of the user is tracked as they walk through the hallways. While tracking the user's location is relatively straightforward, much of the challenge lies in initially determining the traveler's location in the building. As the app is started, the algorithm will hypothesize possible locations all around the building. Here we show a visualization of the algorithm. Each small point on the map represents a possible location for the user, and the color represents the direction they are heading. You can see these points moving about, based on the motion data from the phone sensors alongside the images that are captured by the camera. As the user explores the space, unlikely paths will be rejected, like if that path tries to move through a wall. However, as demonstrated in this clip, without using the visual landmarks that are all around, it can be difficult to pinpoint the user's location for movement alone. The large dots on the map represent signs that are to be detected. For example, in this clip, we use the parking space numbers that are painted on the floor and walls in addition to the exit signs. As the trained model detects relevant landmarks, shown here with bounding boxes and estimated confidence, the algorithm narrows in on the user's current location. Once the system is confident of the user's position on the floor plan, it can begin to provide navigation instructions to the user in order to reach their final destination. Funding comes from grants through NIDLR and the NIH, as well as the Smith-Kettlewell Institute. For more information, please visit our website.